Welcome to our Net Zero Waste Design. My name is Kyoung-Hee Kim, and I am a professor of architecture at UNC Charlotte. This session will go over the principles of net zero waste design and its role in circular economy. The annual municipal waste worldwide stands at 2.1 billion tons. A substantial fraction of the municipal waste is non-recycling, which is buried in landfills or incinerated. In other words, our current society operates unsustainably as a large landfill and incinerator. Building-related materials account for a large portion of waste generation that ends up in landfills. In the United States alone, 615 million tons of solid waste were generated in 2008, with 455 million tons, 74%, being construction and demolition, C&D, waste. Only 20 to 30% of C&D waste was recycled or reused, while the remaining was discarded. This scale of C&D waste underscores the need for a circular economy of collection, reuse, and recycling of building materials. This slide examines how a building's life cycle works in a traditional linear model. On the input side, in the building process, we consume raw materials, energy, and water. On the output side, the building produces pollution to air, water, and soil, as well as waste materials including solid waste and liquid effluents. The slide explicitly labels these stages as inputs building life cycle process output, illustrating the one-way flow of resources. We take resources in, use them through the building's life, and then dispose waste and emissions into the environment. To counter this, several circular strategies can be applied throughout the building life cycle. These include reducing resource use, using less material or designing efficiently to create less waste, and choosing renewable resources when possible. Another strategy is to sequester pollutants, capturing carbon or other emissions so they are not released into the environment. Then we have recycling, processing waste materials into new materials and reusing components again instead of throwing them away. I would like to highlight that to achieve zero waste, we must consider the building's entire life cycle and intervene at every stage, reducing input, reusing and recycling materials, and mitigating outputs in line with circular economy principles, as we will discuss in the next slide. This figure explains the difference between linear economy, recycling economy, and circular economy. Linear economy on the left is take-make-waste, where resources are used once and discarded. Recycling economy in the middle is an improvement over the linear economy, but it includes a recycling step and still relies on waste production. Circular economy on the right creates a closed-loop material cycle through reuse, repair, and recycling, which reduces waste and maximizes resource efficiency. Achieving net zero waste comes from circular mindset. It continually cycles resources and regenerates natural systems through zero waste design, rather than constantly consuming new materials and dumping old ones. Now let's look at the net zero waste approach. Circular economy prioritizes reducing waste during building construction, operation, and demolition phases, while regenerating building materials for sustainable future use. The reduce side aims to minimize waste generation during all phases of the building's life cycle. This involves strategies like efficient material use, modular construction, and avoiding oversizing. The regenerate side focuses on recycling and reusing materials, such as salvaging C&D waste, repurposing building modules and systems, and implementing adaptive reuse techniques to transform old, low-performing buildings into sustainable, innovative buildings. Net zero waste design incorporates a waste-free, closed-loop system where waste becomes valuable resources, supporting the circularity goal. Additional videos on circular economy and sustainable materials are available. Now let's look at how the circular economy is applied in building construction across different scales. This graph explains the relationship between environmental values on the horizontal axis and economic values on the vertical axis for different recycling and reuse levels in building construction. Reuse of building elements such as bricks has relatively lower financial and environmental value. Reuse of building systems like structures, mechanical systems, or facade systems provides better value. Reuse of the building modules, which retain significant portions of a building structure, further enhances economic and environmental benefits. On the far right, the reuse of an entire building, also known as adaptive reuse, has the highest economic and environmental value. This is because both economic and environmental values improve significantly as the scope of recycling and reuse expands. This emphasizes the importance of adopting broader circularity in the built environment. Next, let's look at recycling materials. The circular economy diagram on the left illustrates how recycling can transform disposed waste into building materials. The example on the right highlights an innovative material developed by UPM Biocomponents in Finland in collaboration with Shigeru architects. The design team recycled label printer waste and turned it into load-bearing, waterproof building frames and construction panels. Recycling reduces waste from consumer products and creates high-value construction materials. This example highlights how a type of industrial waste is ingeniously repurposed into a construction component. This slide illustrates the reuse principle. The circular economy diagram on the left shows how reuse reintroduces existing materials into use. Reuse preserves material value and avoids the need for virgin resources. The example on the right features the People's Pavilion in the Netherlands. The pavilion was built with salvaged timber, steel, enclosures, and modular components. After the event, all components were taken apart and transported to different event venues for continuous reuse. Finally, regenerating or replenishing resources can be another design principle for the circular economy. Using microalgae as a biocoating developed at the University of Surrey in England envisions algae coatings that use carbon and produce oxygen for space applications. Now we turn to an example of regenerative design solutions that not only reduce waste, but also create a net positive effect by regenerating resources or ecosystems. The key point in including this example is to stretch our imagination of what's possible when we think regeneratively. Push Slab 2014 integrates zero-waste principles throughout its design. 1. Reduce strategy. The building's timber facades are constructed from FSC-certified wood sourced in France. The use of timber facades helps reduce the environmental footprint and allows the cladding system to be reused or biodegradable at the end of life of its life cycle. 2. Regenerate strategy. The building also incorporates sophisticated systems that align with zero-waste goals. 1,500 square meters of solar panels on the roof power the building with less reliance on fossil fuels. A grey water recycling loop dramatically reduces freshwater waste. For net zero energy design, Pushed Slab was the first building completed in Paris's first eco-quarter, operating at just 25% of the typical office's energy use. Pushed Slab was configured with several localized cores and a flexible space layout to allow for spatial adaptability and ease of accommodation across a variety of tenants, helping to mitigate major structural alterations. Pushed Slab's timber construction, grey water recycling loops, solar systems, and adaptable design highlight net zero waste principles within an urban context. High Alpine Hut Network 2019 is a project that embodies net zero waste principles. This compact, multi-story Alpine hut features mass timber and CLT panels using locally sourced wood that stores carbon. 1. Reduce strategy. The material choice achieves net zero waste goals by using prefabricated timber and CLT, in which structure is erected with minimal cutting and material waste. The foundations are extremely small, only 12 meter by 7 meter, with minimum concrete use and disturbance to the site, essentially using less material from the start. During its operation, the hut implements closed-loop systems through using waterless toilets to handle waste on site and avoiding sewage discharge. 2. Regenerate strategy. It also relies on bioclimatic design, efficient systems, and solar design featuring solar panels and solar water heaters for energy, further minimizing external resource needs. The building surfaces are designed to collect rainwater to offset water use from water-saving fixtures. The high Alpine hut exemplifies them from its renewable timber structure to its tiny footprint and self-contained waste systems. In sum, this precedent demonstrates how designing with modular wood construction, local materials, and off-grid waste handling can significantly move a building towards zero waste. The Gaia Building 2022 is a campus facility that aligns with zero design in materials, carbon, and energy. 1. Reduce strategy. Gaia's superstructure was constructed from mass timber and CLT. The structural bays measured 5 meter by 11.5 meter, with CLT spans of around 3 meter between beams. A high level of off-site fabrication sped up construction and drastically reduced material waste from on-site cutting and fitting. To further cut down on waste and carbon-intensive materials, concrete use in Gaia was limited to essential elements, including foundations, shear walls, stair cores, and wet areas. 2. Regenerate strategy. Walls were built from salvaged brick from the former building. The trees harvested for its glulam and CLT had sequestered around 5,845 tons of CO2, which significantly reduced the project's net carbon footprint. Moreover, all timber was locally sourced from sustainably managed forests, and more trees were planted than were cut down for Gaia. The Gaia building embodies the principles of net zero waste in a practical form by reusing, restoring, and renewing resources. Net zero waste prompt. As we conclude, reflect on how these net zero waste strategies can translate into your own design work. Consider how a flexible floor plan and future adaptability help net zero waste. Consider cradle-to-cradle material strategies and resource cycling without waste. Consider reuse or regenerating resources. Design a building where material, systems, and space design contribute to a closed-loop, zero-waste outcome. This video was supported by UNC Charlotte in collaboration with the US-ASEAN Smart Cities Partnership. For further inquiries, please contact Kyoung-Hee Kim at UNC Charlotte. Together, we can advance towards a sustainable and net zero future.